we're happy to have Yifan Chen from Quran Institute at NYU to speak in our seminar. So Yifan got his PhD from Caltech last year, and he's now a Quran instructor at NYU. His work has been spread in a lot of fields in applied mathematics, in particular in data science, certain quantification, numerical analysis, and scientific computing. He's going to talk about efficient approximate sampling for high-dimensional scientific computing. Thanks, Yifan.
Thanks, Milong. So hello, everyone. So my name is Yifan. I'm now a post at the Quran Institute at NYU. And first of all, I want to thank the organizers for inviting me here. So it's first time to be in Minnesota. It's a great pleasure. And today I want to tell you a bit about my recent research on sampling algorithms, and with some motivation, with some theoretical motivation from high-dimensional scientific computing, and with some applications in those fields. So let me first set up the stage, the context. So the classical sampling problem, the goal is just to draw some samples from a distribution that's denoted by pi, and sometimes also denoted by exponential minus v. V is a potential function. So the pi and v here may be directly modeled as data, modeled as a physical model, or they may be learned from data. So such a problem are very classical. They have a lot of applications, say molecular simulation or the Bayes inverse problems, where you get a posterior distribution and you want to draw samples to do statistical inference. So the challenges of this problem, or one of the challenges of this problem, is that we may need to deal with probability distributions in high dimensions if the state space X is a big number or big state. So it sometimes can be computationally very hard to traverse or to navigate this high-dimensional probability distribution space. And the latter method has been proposed in the literature to solve this problem. So say the classical Markov-Chain Monte Carlo method and the sequential Monte Carlo method. So most of them, they lead to some dynamics in the space of probability measures. And if you run the dynamics, and eventually you end up with some approximation of this target distributions you want to sample. Particular instance includes the stochastic differential equations. So you have the dxt equals some drift dt plus some diffusion coefficients. So under this framework, so the questions or the task one can ask is, how do we design the BT and sigma t? So given a task, given a special or specific target distribution, how shall we design this BT and sigma t to get better algorithms? And also, since this is a continuous dynamics, the lateral question or we must address is, how do we implement it in practice? So how to discretize it? So, and because now we are interested in problems in high dimensions, then all those questions will be put in the high dimensional context. And today, the talk will contain two parts. So related to the question raised up in the last slide. So the first part, I will talk about, about the numerical implementation. So it's about the localization phenomenon, which implies that the discretization errors that are linearly dimension-free, even you are in extremely high dimensions, the errors in individual coordinates, they are not independent, they are not dependent on dimensions. So this is for some Langevin algorithms and with motivations from the molecular simulations, because there you have billions of items. So you really want to have some dimension-beline convergence rates. The second part is more about the data-driven part, where so nowadays people use diffusion models. The specific applications for those models is for probabilistic forecasting. Here I want to show you that a very interesting process, the Fomer's processes. They give a statistical optimal design, so in some sense, of the diffusion coefficients. So we'll address a little bit about the design questions. So I will start with the first part, and feel free to interrupt me if you have any questions. Okay, so for this sampling task, perhaps the simplest approach, simplest stochastic dynamics we can come up with is the Langevin dynamics, or overdamped Langevin dynamics, where you have the gradient part, so it's a gradient flow, you plus some Brownian motions, so that under my assumptions, as time goes to infinity, and the samples or the particles will converge to the stationary distribution. So if we run this simulation, we get some approximate samples. In practice, we need to discretize it. And the simplest way to do this is just by Euler-Maruyama, which means we get the forward Euler for the drift part, and we plus square root 2 times the Gaussian noise with correct covariance. So it's well known that this scheme is biased, meaning that even you run k to infinity, it will converge to some stationary distribution pi h. that will not be equal to pi. So there will be some discretization errors intrinsic to the scheme. We can always correct the bias by using Metropolis adjustment, which means every step when you do the proposal of the unadjusted schemes, you accept it with some probability. So this probability is calculated by comparing the density ratios. So the classical Metropolis Hastings algorithm. If it's larger than the ratio, we accept, otherwise reject, and we propose again. So this is known as the MALA, Metropolis-adjusted Langevin algorithms. So there are also other recent developments in the theoretical computer science literature that use the proximal sampler with inspirations from proximal optimization method that are also unbiased and similar theoretical results. So there are many possibilities to turning this continuous dynamics into an algorithm that we can implement in computers. Since our motivation or our problem of focus is high-dimensional problems, so it's natural to ask, so how do they perform in high dimensions? We can have a very toy, say, implementation to say what happens when dimension increases. So for this figure, we just implement the unadjusted Langevin and adjusted Langevin for Gaussian targets, so the simplest distribution we can imagine, and fix the step size h. The x-axis is the dimensions, and we see the dimension grows from 10 to 1000. The left y-axis is the Washington 2 bias. So Washington 2 is a metric measure distribution in distance. So the bias means the Washington 2 between pi and pi h. We see the green line just grows, and the bias depends, for this figure is square root d, dependence on dimension. And also on the y-axis, on the right y-axis, we have the acceptance rate of the adjusted Langevin. So we know that for adjusted Langevin, it's unbiased. It will eventually converge to the truth, but sometimes you may reject a lot of samples. If the acceptance rate is very low, that means it's less efficient. So here you can say when dimension grows beyond, say, 10 to the 3, the acceptance drops. And if you improve the dimension further, it becomes very, very small. So this, like a very illustrative example, says that the step size must decrease as dimension increases. So it also means you need more like a computational cost in high dimensions. And the lateral question will be, what should be the scaling h regarding d to make, say, both algorithms work in the high dimensional case? So this is also classical problems, and many theoretical results have been done in the literature. For the MALA, h needs to be small for the high acceptance rates, as we discussed. So theory in the literature suggests h will proportional to 1 over d to the power of 1 over 3. So this is done in the last, I think, more than 20 years ago, using the diffusion limit argument. So it's a asymptotic argument. And recently, there are some results in the TCS community. They do long asymptotic guarantees. And but they get similar rates. It's 1 over d to the power of 1 over 3, 1 over 2, or 1, depending on the assumptions on the distribution. And here, one thing to note is that this scaling is not avoidable in general, because for MALA, you always need to compare density ratios to get the acceptance rates. We know that when dimension is high, density is a difficult object to deal with, because in infinite dimensional case, in the extreme, there is no Lebesgue measures. So if you compare two density in high dimensions, you will get some small large numbers. So you must need a very small step size to make it non-negligible. Similarly, for unadjusted Langevin, h needs to be small for small bias, and the theory in the literature suggests similar scaling. H scales like 1 over square root d or 1 over d, depending on also on the assumptions of the distributions. So those two results suggest that in high dimensions, h needs to decrease like this power law. So this scaling is not that bad because it's just a square root d, not exponential, but not say exponential small in d. So when d is, say, 10 to the 4th, for example, you are dealing with images 128 times 128, this seems okay. But for applications, say, in molecular dynamics, you may have billions of items. So this looks like a still very restrictive. Indeed, so there are some empirical observation I learned from those molecular simulation books. So in those molecular dynamic simulations, so they deal with similar sampling problems, but their potential may be much more complicated than the potential covered in the theory above, because there are many physics interactions there. So they use very similar unadjusted integrators. So they use unadjusted HMC for billions of items. But there, they typically employ a fixed step size of 0 femtoseconds. Basically, this the step size makes the unadjusted Langevin stable. So once the stable is, they didn't create some, say, blow-ups, and then people just use this, no matter how large D is. So even D increases, we keep the step size that makes the system stable. So this seems to contradict with all the existing theory, because existing theory says that if you don't decrease regarding D, then you may get large errors, and so it may not be reliable. And there has been some work in the literature suggests that an H equals order 1 without decreasing could still work if you are only interested in some specific observables. For example, fx, the observable, equals to the average over all coordinates. So this is like the concentration phenomenon. You have many randomness in all the coordinates, but you average them, you only get the core scale features, which you have a smaller accuracy, smaller errors. Another way to say this is the gradient of this, and the observable is scales like 1 over square D. So we know that Watson metric, they measure the errors like between all the Lipschitz one functions. So here the Lipschitz constant scales 1 over square D. So this one just compensates, and they just kills the errors in the unadjusted Langevin. So if you are interested in the average observable, actually you can do much better. But sometimes in the, say, in the particles, maybe you're not interested in the averaged accuracy. You may only be interested in one particle accuracy. So you have so many items or so many molecules, you may want to know what's the accuracy for one of the items. So that's not covered by those theories. So in our work, like we obtained the following theorem, and it's a delocalization of bias phenomenon, saying that for unadjusted Langevin in D dimensions, the step size equals to 1 over K, capital K, could suffice for desired accuracy for all K marginals. So what are K marginals? So K marginals are just marginal distributions of any K coordinates. Suppose you have 1 billion of items in the distribution, but you only select K item of them, that they also have the corresponding marginal distributions. We call that K marginals. So here, for this K marginal here, we say for any K marginals, so not specifically one of the K combinations. So this result is stated rigorously under assumption that the distribution is log concave and is log smooth, and we require way is Gaussian or has some sparse interactions. And we do have some generalizations, but for those cases, we can do the most clean results. So if this holds, that means the iteration complexity is not no longer depending on D, because the step size order 1 over K, and the overall complexity will scale with K rather than D. So you get some dimension-free results. So this is the work with Yifan Chen and with the PhD students in Kurang, and Jonathan elsewhere, Jonathan Weir, are professors at Kurang. So if we take K equals to 1, just means we're interested in the one particle accuracy. They just say that the bias of the unadjusted algorithm in each individual coordinates just scales near dimension free. So even you have billions of, say, variables, but the one particle density, the accuracy is still very good, even without decreasing the step size. And we refer to this benign dimension dependence phenomenon. We call it a delocalization bias, because overall, if you think about the distribution, say the simplest case, the product measure, the whole bias will be scaled with D, because each of the dimension you will have some bias due to the discretization of Brownian motion. But here it says that the one-dimensional coordinates, the bias actually behaves very well. It's just like it's like a product measures, so it's dimension-free. And this phenomenon is not shared by any unbiased algorithm, such as the MALA, where you must decrease the step size to ensure the acceptance rate is non-negligible. So any questions regarding the statement of the theorem? Okay. So assuming that's true, and then we will get updated figures for the performance of the algorithm in high dimensions. So those green and the black curves are for the Watson bias and the acceptance. The red curve will be the corresponding bias if I'm interested in 1D marginals. So we got the flat curves. It didn't increase with dimensions under the assumptions of our theorem. This also applies for K marginals if K is independent of dimension, because it only like moves the line a little bit upward, but it didn't create a slope. And this shows that the approximate and the unadjusted approaches can be more scalable compared to the biased approach. It also justifies in many applications, people don't do Metropolis algorithms because they didn't scale that well with dimension. So let me show you, say, how do we analyze these results? So for the classical analysis, people use the Wasserstein-2 metric to measure the distance between distributions. And this is the definition of the Wasserstein metric. So WP, mu nu, and are just two measures. It's a minimum of x minus 1, the 2 norm raised to the power of p. And we have the gamma. Gamma is the coupling between the two distributions. We find the optimal coupling between the two distributions, and we take the power like 1 over p. This is the WP metric. As you can see here, the x minus y to the power of p, they just measure the 4 coordinates. So every dimension will be taken into account in this formula. And in our analysis, we propose to use a different metric, the Wasserstein P L infinity metric. So based on argument that the L infinity, in contrast to L2, they can measure like a small set of variables. So what do we mean? So this is the definition of WPL infinity. We just replace the 2, the subscript 2 by infinity, which means now things in the bracket is just the infimum norm of the difference of the 2 vectors. And we have the following very simple inequality, which says that because the infimum norm is the largest among all the coordinates, so k times the largest will be larger than any k combinations. That's the definition of the maximum. So once we have this, we can plug this into the above 2 formulas, and we just do minimization on both sides. Then we get the bound that k to the power of 1 over p times the WPL infinity norm or distance will upper bound the WP distance between any k-dimensional marginals mu and nu, because due to this inequality. So this any k-dimensional, you have only the k coordinates, the difference. And the infinity norm will bound this. So once we have a analysis or a bound on the WPL infinity norms, we can quickly turn this into the bound on any k-dimensional marginals. So that's how we measure the accuracy of the k-dimensional marginals. And in this work, we consider p equals 2. So once we figure out the metric to measure the accuracy, so that we're able to understand how the algorithm performs in low-dimensional marginals, we can try to use this metric to say some examples. So the simplest example we can consider would be the distribution that product measures, or equivalently, the potential function Vx. They decompose into individual potential functions at each coordinates. So this is maybe the simplest case we can imagine. There is a delocalization of errors, because for this potential, all the particles that are independent, they didn't talk to each other. So we can expect individual accuracy only depends on that coordinates without dependence on dimensions. And here with the assumption, like the log concave assumption again, we can show that that's indeed the case. The W to infinity bias between the pi h and pi will scale with log 2d rather than d. So here, if we replace the W to infinity by W2, and the standard W2 will get the log 2d replaced by d. But here, use the L infinity, we get log 2d. Okay. So this means that for this metric, you get some benign dimension dependence, and this in turn implies that the W2 between any k marginals of pi h and pi is order kh log 2d. So h will only be 1 over k up to log d to get the desired accuracy in this k marginals. So, but this case for the product measure case is very intuitive to understand, because every particle didn't talk to each other. So what can be better than such a case to expect delocalization. So on that, so the proof for the first case is not that difficult. It's the basic coupling argument, and because now everything is independent, so all the basic arguments can go through. Another interesting case will be for the Gaussian measures. So for Gaussian measures, we know that the Langevin algorithm turns out to be the OU process, which we have the explicit formula for all the iterates. Say consider the Gaussian case will just be a quadratic function, and the log concavity assumption turns out to be the precision matrix between alpha and beta. And use this explicit formula in the Gaussian case, we can just calculate the what's less than 2 infinity metric between the two distribution, and we get similar things. But here it's tighter. We don't have the condition number, beta over alpha. But again, we say that there is a log 2D. So if we use the previous metric without infinity, we get the HB here. So it just goes from D to log 2Ds. And the same result applies the what's less than 2 between any k marginals of the bias distribution and the true distribution only scales with log 2D. And you only need H to be 1 over K to ensure a bounded bias, no matter how high the dimension is. And this justifies the effect we are talking about, the overall bias that linearly delocalized across all one-dimensional marginals. So all the errors are a lot, but the individual actually are well behaved.
Understanding the advantage of this new metric. I'm confused by that. I expect the upper bound, but why this metric?
So here, I think the argument is, the intuition is that we have the bias distribution pi h and pi, and we know that the what's less than 2 metric, the bias will grow with D, because you have D dimensions. Each individual coordinate has, order 1 contributions. Then we ask for, if we only interested in some low dimensional marginals, say we only look at 3 coordinates, maybe we get something dimension free. And we need a metric that can capture that. But what's less than 2, they sum over everything, so they can't do that. And here we use WPL infinity because it's a metric, because if we only look at the 3 coordinates, we know the iterations will always involve other coordinates because they are coupled. So we cannot just measure that individual coordinates directly. That's why we use L infinity that just bounds everything by maximum. And this serves as so this works. So I think the choice of this metric is just like the analysis tools, a way to bound those distance. Okay, thanks. So any other questions? Okay, so those are most analysis. I will, in the second part, we'll talk about more about some experiments. So those 2 examples say that, okay, there is the delocalizations. So it means that if you look at the one-dimensional thing, everything sounds great. But does this effect holds in all the cases? Unfortunately, the answer is not. So there are some examples which we didn't get delocalization. So what's the example? So consider pi tilde equals to Q push forward pi, and Q is a rotation matrix which rotates every coordinate so that the first coordinate will be 1 over square D and sum of xi. So basically, this is the maximum the separation you can get for rotation matrix, so that once you apply this Q, you mix every coordinate with the maximum amount. And we take pi to be rho to the power of D. So rho is a 1D center distribution such that the mean of rho and the bias of the H differs by delta. So rho is a one-dimensional distribution, and it also have a bias rho H if you run the Langevin, and we suppose they are different. So this will not be covered by Gaussian. For Gaussian, you always get the same mean, but in general, you can use Gaussian mixture to get the bias there. The mean will differ by delta. Then the claim is that for such a pi tilde, we get the W2L infinity scales at least square root D. So the argument as follows: because the Langevin dynamics, they are equivariant to rotations, So we get the bias distribution also Q push forward pi h. So in that case, if you measure the first coordinate accuracy of pi theta and pi theta h, we use the definition of push forward. It will be f times the pi minus pi h. So f will be 1 over square d, the summation of the xi. And because for rho, each dimension, we get delta discrepancy, and there are d coordinates, so we get d delta, and we only scale down by 1 over square d. So eventually we get a square d delta for this observable. And for this observable, the accuracy will be upper bounded by the Wasserstein bound, because Wasserstein bound takes care of all the Lipschitz observables. So eventually we get the Wasserstein to L infinity distance also at least square root d. So for this case, there is no delocalization, but instead, so all the bias across all the dimensions, they will be concentrated on one coordinate, which is the rotated coordinates, because we rotate everything into that coordinates. And on the other hand, this example also suggests that if you have very strong correlation or strong interactions in one coordinate, then you may not expect there is delocalization. You may expect there is a concentration. So motivated by this fact, a natural question to ask is that can we get delocalization if there is a sparse interactions? Because we say last slide, if there are strong dense interaction, we get concentration. But if there is sparse, maybe we get some hope, because sparse means that every particle only talks to a small number of particles. So eventually, you may only be influenced by a neighborhood, but not the whole thing. So the bias may only depend on the neighborhood size. So this is the main results in this work. So we show that the W to L infinity bias for the sparse potential illustrated here. I will explain in detail soon. So if V is such kind of potential and V is log concave, then we can show the W to L infinity also scales only logarithmically in D. So that means that even D is billions of log D is just a very small amount. So what's the potential we consider? It's inspired by many physics models. So here, suppose it's a 2D lattice, and each of the grid points in the lattice represents a variable and represents one dimension. And the central part, we say it's the S variable xi. And we know that the less dark blue region will be the first layer labels, and the light blue will be the second layer neighborhood. So we can denote by N1 and N2. We assume the potential can be decomposed into the potential of every individual coordinates. So Vi cos I will be the first layer labels. So Vi cos I means that all the force that can be filled by the xi variables. So this Vi only depends on the neighborhood of this variable. And for here, we have the sparsity parameter, which is the size of the neighborhood. So here for the S1 will just be 4. S2 will be bounded by a line because it's a 2D lattice. And for this example, we know the interaction is local because they are defined by the lattice. And the interaction, the locality increases only polynomially as a k-square. For such case, we can get the logarithmic in D bound with some power, which depends on the growth of the size. So this means once you have a sparse potential or local potential, you still didn't, the global effect is limited. You only get some, like a small amount of local effect, and for one particle or like some small amount of particles, the accuracy is dimension free. Yeah. Maybe it's time. So I won't go into the details of the proof, but let me make a quick summaries of what's the first part. So we are interested in the sampling algorithms, the unadjusted sampling algorithms. We discover a new phenomenon. I think it's the first phenomenon, dimension-free phenomenon for the marginals. It's called delocalization of bias. Basically, the algorithm bias is a lot grows with D, but for individual coordinates, it's just a dimension-free. So this means that we get a linearly dependent step size and complexity, which are very highly scalable. And this phenomenon is not shared by unbiased schemes, like the Metropolis-adjusted Langevin. we prove it for certain cases, and there are also counterexamples. We have some asymptotic arguments which for more generalizations, but we are not going to talk about this here. And we are still investigating this to extend this to more general distributions and also to design algorithms that can specifically target at the low-dimensional marginals, which may be like the interest of like practitioners. So let me pause a little bit to see if there are any questions for the first part. Okay. So let me go to the second part. So it's more about generative modeling, like diffusions, and specifically for probabilistic forecasting. And we talk about how to design this dynamics for some optimized performance. So basically, this probabilistic forecasting or generative modeling is also a sampling problem, but driven by data. So your classical forecasting problem, we can formalize as this. So give a time series, yk tau, k is integers. We want to predict yk plus 1 tau from new yk tau. So that's what you want. And there's a lot of applications in fluid dynamics, whether forecasting or even videos. This is from Sora. And for mathematical treatment, we assume that the success with observation either join the PDF. So this can be satisfied with the Markovian model or when you see at the stationary phase. Given this modeling, given this context, then this problem turns out to be a conditional sampling problem. So once you give me yk tau, you want to sample the conditional distribution, conditional yk tau, what's the distribution at the next time? So that's a problem I want to address. And one way to solve this problem is to just think about how can we move from yk tau to the conditional distribution we want. So there are many methodologies developed in the literature by modeling, so how yk tau can reach the target. So from the generative modeling perspective, so generative modeling always deals with how do you transform from Gaussian to the target distributions. So here we can say, how do we construct stochastic dynamics that goes from the Dirac's to the target distributions. So it's a bit different, but quite similar to the Gaussian distribution. If you make the covariance shrinks, it will become a Dirac. So here is like the extreme case where you want to build a generative model which accepts yk tau as the input and then output the conditional distribution condition on yk tau. So that will be the ensemble forecast you expect at the end. So how do we deal with this problem? So as we know, if we want to do generative modeling from Gaussian to target, there's diffusion models, score-based diffusion models. And there has been some recent development using the whole class of flow and diffusion-based generative models to achieve this task. A particular one is called stochastic interpolants, developed by Michael Bergel and Eric Van Eygen and Nick Buffet, so in the Courant group, and also similar works like flow matching. So let me describe how this is achieved. So for notation convenience, we let x0 and x1 denote the current and forecasting state. So you want to go from x0 to a distribution of x1, conditional x0. So that's the goal we want to achieve. And the methodology goes as follows. So we define our stochastic processes, IS. So I means interpolant. IS equals to the linear combination of x0 and x1. So alpha S and beta S. And we'll add some diffusions to make this more regular. So alpha 0 will be 1, and alpha 1 will be 0. Beta 1 will be 1, beta 0 will be 0. So that we eventually get I0 will be your current state, and I1 will be the forecast state. Okay, so it's just like you connect them by a line, but with some diffusion to tweak the dynamics. And x0, x1, they're just joint distributed by the joint distribution, and W here is a winner processes. So why do we define this stochastic interpolants here? So we know that the boundary of this interpolant process will gives us the current state and the forecasting state. So if we can simulate this process, then we can do the forecasting. But this is not doable because this IS is not Markovian. It always depends on x1 in order to give any results. But it turns out that there is a stochastic differential equations that will give the same output as the that will give the same iterates with the same marginal distribution as the IS. So what is the stochastic differential equations? It will be dxs equals to bs, some drift, plus sigma s dws. So here bs will be of this form. It's a conditional distribution. And it holds that the law of the xs solution to SDE is the same as the law of the interpolant process. In particular, the law of xs at time equals to 1 will just be the conditional distribution. So that means if you can simulate SDE, now it's Markovian. Then you do the forecasting. So it just matches the figure here. If the green line now becomes the stochastic process which you can simulate. If you can simulate it, and you can get some samples from the target distribution. So here, so this actually fact is very simple. There is no like deep math here. So if you look at this, the stochastic process defined here, IS, we can just differentiate both sides. Then by Ito calculus, we get DIS equals to these terms plus some diffusion processes just by chain rules. Okay. Once we have this, we know the drift term here is not, say, Markovian. It didn't depend on IS. But say what's the best we can do to turn this into a Markovian or a function depends on IS. So we know that for IS, suppose I'm currently in IS, and we know all the drift terms will be described by this expression. And suppose I'm at IS, then the best drift we can do is just to take the conditional expectation, because we get an ensemble of vectors. And when at IS, I will just condition IS equal to the current point, and we average all those vector fields. And that gives this BS. So rigorously, we can just prove this by just integration by parts. So it's just like once you define an interpolant process, you have a BS. And once you know the BS, you can use this to simulate the dynamics and then get a forecasting. So the question will be, okay, how do we learn the BS? So it's the same story as the diffusion models. This is a conditional expectation, which means that you can write it as a minimizer of the square loss regression. So here we can write down the following loss function. So the drift BS you want will be the unique minimizer of the following loss function. This is the BS hat IS x0 minus the term you want to condition on. That's just the quadratic minimization characterization of conditional expectation due to the L2 optimality of conditional expectation. So this is just a loss function you can use. And then you can say that for this loss function, if you have data x0 and x1, then you can evaluate it and you can just optimize it. And the diffusion models, people often argue or like advocate the advantages of those loss functions is that they are simulation free. Simulation free in the sense that so for the loss, there are some stochastic processes, the WS here. So in practice, if you have a stochastic process, you may need to simulate this WS so that you can evaluate the loss functions. But here, because you know the WS in distributions is like square root S Z, so you can just directly sample Z and put a square root S Z here, and this can give you this loss function values. And then you can parameterize this by neural networks. And if we believe based on the common premise that many neural nets, if you design it correctly, you can be very expressible and you can represent the thing you want to represent very well. And based on also the premise that we can optimize it very well. So this is the algorithmic framework. We have the loss function for BS, and if you optimize it well, then you get the approximation of BS, and then you simulate it, you can get the forecast distributions. So any questions before I move? Let's see some examples. So this is a very simple algorithm. So let's say how it performs given a synthetic example. So we consider the example the 2D Navier-Stokes equation for fluids with stochastic forcings to create some randomness in this equation. So this is the vorticity formulation. So omega is the vorticity of the fluid, and we have the viscosity nu, and we have some damping terms to damp this so that it converges to stationary phase fast. And we have some eta, which are the random forcing. So it acts on some Fourier modes. And for this model, so it's a mathematical model. So we can show that it's ergodic so that you have a stationary distribution. So everything is rigorous, just as an example to test the algorithm, how it performs. And the goal is to give the current vorticity, which are some flow field. We want to forecast the vorticity after 10 tau. Tau is the lag, and under stationarity, because it's ergodic, we assume it's in stationarity. We want to forecast. Okay. And this is one of the results. So the left-hand side figure, the left up corner is the omega t. So you can say a lot of chaotic, and it's just the fluids. And the result output by our model is the X-ray with vorticity fields. You see they have different shapes, different patterns because it's stochastic. So that's expected. We can average them to get a mean and also conditional mean and also conditional standard deviation and compare it with the truth. So the left-hand side is the truth. Right-hand side is an approximate surrogate. And we say for the mean and standard deviation criteria, you do get something quite similar. And here you say for the mean, actually it's much darker than the real omega t plus 2 because there is random noise. The uncertainty has energy. If you average it, you ignore the stochasticity, so you get something that's completely different from the fluids. So that also means that for this problem, you must use probabilistic forecasting. If you do deterministic forecasting, the best you can hope is the conditional mean, but this just didn't give you the correct flow fields you want. And there we take a lag equals 2. So when lag is 2, it will needs to autocorrelation for time series 10%. So this justifies that this task is not trivial. And we are doing this for resolution 128 times 128. And we use 200,000 data for training a 2 million parameter unit, and we just get this results. And because it's a physics problem, it's not an image problem, you do want to say if there are any physics you can preserve. So one way to test this is to look at the spectrum of the fluid. And here is the entropy spectrum. You can think it as you take the Fourier transform and you look at the energy at different wave numbers. You get a curve. And for such case, we say the true and the forecast, they matches pretty well. And for this forecast state, we can think it also as a surrogate dynamics that we don't need to simulate the Navier-Stokes, but we just simulate the surrogate SDE to solve the equation. And from this perspective, we can ask what's the efficiency compared to simulating the PDEs. And for this example, we get 100 times faster because you can use larger step sizes. And you can also do long time errors if you like roll out, which means you take the omega t plus 2 as your initial point, and then you roll out. So after some time, you may get a lot of predictions. In general, when you roll out too much time, it may fail because it's a chaotic dynamics. You can't expect you get everything after a long time. But in our experiment, we found that if you only look at the total entropy, which is the scalar quantity, that is the average total entropy, and you still get good results. That means that a long time it stays around the invariant manifold we expect, that still the entropy is accurate, but maybe the individual trajectory won't be. And this is another example for which we do both super resolution and also forecasting. We go from omega t from 32 times 32. We want to forecast the conditional distribution omega t plus 1, conditional omega t on a higher resolution, and you get some also similar results that looks visually good. And if you test the spectrum, you also get the spectrum and the good spectrum. So here you may think it's a bit magical. You can go from the coarse scale and recover all the fine scale. So this is not possible for individual pictures, but statistically it's doable. That's how, like, if you do everything statistically, you can actually capture the statistics, but not individual samples. So any questions regarding the experiment?
How long do you take? Just one step?
Here is omega t plus 1. So there is a reference that if the lag is 2, then autocorrelation is 10%. So basically for 1, like maybe 20 to 30%. So step size. So here, so once we talk about say how long we must have the reference. So what is the unit? And for the Navier-Stokes, when we integrated the PDE, we use time step size 10 to minus 4, because that's the one making it stable. So here tau equals 2 means that you take thousands of steps later. That answered the question.
So for the training, you also do this. Let's say you have U0, you have U1000. That's
Mhm.
training.
Mhm.
Or you have the 0 and U10RT.
So in training, like we simulate this stochastic PDE a long time, and then we pair omega t and omega t plus tau. So that means that omega t, and after thousands of steps, omega t plus tau. And that's a data pairs. And you want to go from omega t to omega t plus tau. Okay.
So can you use like multiple, like multi-lag, for example, use xt minus 1 and xt to predict xt plus 1?
Oh, yeah, that's a very good question. So if it's Markovian, then it's not necessary.
Yeah.
But in practice, I think most examples, they may not be Markovian. So if you put all those more conditional distribution, more conditional information into it, you get more accurate results. Yeah, we didn't do it here because for this example, just use xt, condition xt, we get reasonable results. If you do more, you should get better, but also it's more costly because your condition are more like 2 images or 3 images. So it's like just the network will be able to handle the conditional information. So it's more costly, but I think it will be more accurate. Okay, thanks. Any other questions? Okay, yeah, let me. So okay, this is still some math. So let's look at some figures. There is also some place we can play with some math. So which is returns to the design questions of the SDE. So in the score-based generative models, there is a fact that once you get SDE, you can always choose the drift and diffusion terms for free, which means that the DXT equals to BS plus sigma S DWS. They have the same law as another SDE. So we denote it by XSG, PSG, and GS. So where the BG will be BS plus some scalar times the score function, okay? This is based on the fact that the drift term will correspond into the transport equation, divergence zone, gradient zone, equals to, if you do the calculus, this will equal to Laplace though. So it means that the diffusion can be emulated by transport. So this means if you change the coefficient in front of the Brownian motion, which means you change the diffusion terms, you can compensate it with some transport terms, which relates to the score. And this score is a conditional score. And in this problem context, we can get some formulas showing that the score can be represented by some transformation of the BS. And so those detailed formulas are not very important. But the message is that if you give me an estimator BS hat, then one can easily derive BSG hat using this BS hat. So it means that the second SD is also estimable. So in that sense, we obtain a family of SDs and it can be used for generation purposes. So you can always do this trick. But then the question is that, okay, you get many SDs, then you may ask, so which one is the best you want to pick? So you do want to have some optimality. And it turns out that if we consider a specific criteria, which is the KL divergence, it's a criteria for measure distance, it's not a distance, but measure the discrepancy between distributions. If we consider KL between the path measure of the whole path trajectory of XG and the XG hat. And then we can show that, interestingly, the KL is minimized if you set GS to this very interesting formula. So here, note that for the KL between the path measures, so they actually take all the paths into account, but eventually you may only be interested in the KL between the process at the end, because that's the forecast so you want. But this KO between the path measure serves as upper bound for it. And here for this formula, one interpretation, you say the IS equals to RS x0 plus beta S x1. So this ratio beta S over square root S delta S will be the signal to noise ratios, which means that if this term grows very fast, you want to diffuse more. So maybe because it grows fast, that you are learning some signals and it's easier to make mistakes. And use diffusions, SD is kind of like a amortized or like make the error smaller. And so this coefficient leads to some interesting interpretations that if this signal to noise ratio is not decreasing, then we can show the XGS is called a Fomer processes. So this is some process invested by a mathematician, Fomer, and when he studied the time reversal process. But maybe a more like a well-known term is Schrodinger bridge problems, which is an entropy regularized solution to optimal transport. So the process we just learned in the previous slide is entropy regularized optimal transport when one endpoint is a point mass, which is the YK tau, because we learn the dynamics from YK tau to the distribution of YK plus 1 tau. And what we're previously doing is just learning this optimal transport. And there is a stochastic control formulation for this problem, which we have some prior dynamics, dxx equals to as, ds plus gs dbs. And you want to have a control US such that the energy are minimized. So this is the control formulation for the Schrodinger bridge problems. So the claim is that with data, the dynamics we learn to forecast is just the solution to these problems mathematically. And this provides theoretically a new interpretation of Fomer as a minimizer of the KO of the exact forecasting process from the estimated one. So which seems more practical because compared to statistical inference compared to this one. So this is more like a mathematical properties. Okay, if you do this in practice, you do get some improvements in some examples. So here we plot the density of the forecast and we make it one-dimensional. So every forecast is a field, which is very high-dimensional, but we only look at the total entropy, which is the energy of the vorticity. And we can plot the true one, the one with the sigma s, and the one with the Fomer. We optimize the one, and we compare also with the Gaussian-based ODE model, which is like the flow matching or the diffusion models, where you go from Gaussian to a target, but additionally condition on the current state. And you say like the orange one or the green one with GS a little bit better. Also, this is the number. So the KO between the truth and the generation. So with the original one is 8 times 10 to the minus 3. So with the optimized one, you get like a 3 to 4 times better accuracy. So here they are plus minus because we do multiple rounds and get some standard deviations. Okay, so let me make a quick summary. So we are interested in the sampling problems, especially in high dimensions. So for our first case, it's for classical analysis problem for unjust Langevin, which we want to get dimension-free results. And for the second problem, it's a high-dimensional computing problem, where you want to forecast, but the image size or the vorticity size, they are 128 times 128, so it's not a low-dimensional problems. So the methodologies, we use some dynamics or dynamic sampling to solve those problems. And from a mathematical perspective, you want to understand the design of those dynamics and also the numerics. And the first part, we show there is a delocalization of bias effect, and it gives the first like a nearly dimension-free results that advocates the bias approach can be more scalable. And we're currently working on the generalization of this and also some algorithmic use of this phenomenon. So the second part is for probabilistic forecasting, so for diffusion model-based sampling problems. And we have the stochastic interference or diffusion model-based approach to learn the forecast. And mathematically, we show there is special processes, and which is statistic optimal in the sense of the optimal path measure in a KO. So this is the optimal way of tuning the diffusion coefficients, and it gives the Schrodinger bridge between Diracs and target. And there are more general questions about how to design the interpolation, how to design the dynamics to make it more efficient for practical problems. And thanks for your attention, and happy to take any questions.
Okay, can you talk a little bit about the last part, the generative design questions for the interpreting process?
Okay.
Are you asking like in general how to design this interpreting process, or?
Yes, so for this one, you see, for this framework is very general. You just get give me alpha S and beta S and sigma S to get the algorithm. So for this picture we show, we just use very standard beta S equals S squared, sigma S 1 minus S. But in general, you can ask which selection of those parameters can give you better results, and also like is the linearity necessary, or if you can replace the Brownian motion by other dynamics. Yeah.
Actually, do you know the paper by Yifan Chen and Renan Yao? They have the paper localization framework.
Oh yeah.
They have like a very general framework, like how to design this process.
Yeah, but that one, so I'm not that familiar, but I think Yifan Chen, they did the analysis result. They want to show I mean, there are some big conjectures. They use the localization schemes to turn the log concave measure to some measure that's healthy.
I'm not talking about the PLS conjecture.
Okay.
Yeah, I'm talking about the later work with Renan Yao. They have
Okay.
this localization framework. It's the setup is very much the same. It's especially they call this a linear term. It's called linear tubed localization process. Yeah, I'm curious.
Yeah.
I'm curious how this different from that one.
Yeah, I think for the stochastic interference, the specific one will recover the same as the stochastic localization, if that's what you refer to. But there they use it for, I think, analysis purposes. Some people use it for algorithmic purposes.
They apply it to this functional inequalities.
Yeah. But here it's more like maybe a generative modeling applications where we just say, given dynamics, we want to say which IS can be more efficiently learned from data and can be integrated more numerically efficiently. Yeah, but there maybe they want to design it in a way that the average, like the measure in a good way, so that the log sorblet constant become better. I think the concepts are quite similar, but I know quite little about that part. Yeah. Thanks for the question.
I have another question for in your first part. There was one part you defined as a sparse state capture. Do you really need this sort of geometry things like you layer wise, first layer sparse state, second layer neighborhood, something? Do you really need this layer wise things, or it's for example, can I talk about this on geometric graphs instead of lattice, two lattice?
Yes, so for general, if you have a graphic model, you can also define the layers. So there exists a definition of layers because you just look at the height of the potential. You look at how many non-zero entries you have. The second layer will just be, the non-zero entry connect to the non-zero entry you had before.
Okay.
So this geometry can be instantiated in the algebraic description. But maybe a more interesting question is that do we really need this to get the localization results? And we are currently working on this because here, for unjust Langevin, if you do multiple steps, it eventually will get more layers, and we want to control that part. So that's why we have these assumptions. If it's a tree, the neighborhood grows exponentially fast.
We
are trying to answer those questions.
Sure.
Yeah, thanks.
One more question about the assumption. So why do we need this to be
So I think log concave is like convenient for analysis, and for log concave means that you get a contraction after several steps in terms of the Boston system metric. So that this pi h and pi, actually there's a statement for infinite times because that's the stationary measure. If it's not log concave, you iterate the process to infinite time, so the error may just grow very fast using simple techniques. So once this is log concave, that means essentially you only need to simulate this process for finite time, and then just contract. So that error will be the error bound here.
Yeah, but I think if you use or conductivity, you can also use a Kalman
Mhm.
get a TV log locally at least.
You mean for locally they are not concave, but outside of ball? Yeah. So that one, I think this may potentially generalize that case. So then maybe use some reflection coupling or more advanced coupling to deal with the errors. Yeah, here we do low concave because it's a commonly used assumption in the DCS community. And it gives the
There's a lot of many interesting.
Oh, yeah. Yeah, that's a very good point. Yeah, maybe we should try more to say, without assumption, can we do still achieve the same results?
Any further questions? Should also ask any questions from the Zoom. Okay, so if you know that's thank Yifan.对，你其实不需要那个每一步都是 constructive 的，你可以局部它有一些 fluctuation，但是你走到很远的地方，它有 constructive maximum confidence.
Yeah, I remember there was some paper, some people replaced the